And we're back into Perms and Comms and the Binomial Theorem. Part 2 is something that I like to call the Mississippi Principle. I call it the Mississippi Principle because one of my favorite teachers in the entire world called it the Mississippi Principle when he taught it to me. The formal title is Permutations with Repeating Objects. And as much as I like to be a math purist, sometimes the excitement's just there, and I can't help but love it. Let's talk about how to arrange things when there are duplicate letters. But first, what if there aren't any duplicate letters? So we've got the word smile. Aw, you should all smile. I'm smiling right now. I wasn't when I started saying the sentence, but I'm doing it now. Take a quick smile break. Excellent. Moving on. How many ways can this be arranged? Now, hopefully we don't quite need to lay out our 5 slots anymore. Just say letter number 1, and letter 2, and letter 3, letter 4, letter 5. We could do that. We could say there's 5 options for the first letter and 4 for the second, third, 3, 2, and 1. But we should recognize that there are 5 factorial ways to do this. And if we need a value out of this, 5 factorial is 120. Make sure you can get here, though. In the word smile, all letters are different. There aren't multiple S's or multiple M's or multiple I's or multiple L's or multiple E's. They're all different. But if we have the word smiles, then switching the positions of these 2 S's doesn't actually change a thing. They'd be different if those S's, if one was like a red S and one was a blue S, then we'd actually be able to see that, but they aren't different. They're the exact same S. And when we swap their positions, we don't create a new word. So we have to account for this some way. The way we do this is that we take the number of arrangements in general, whatever number of characters we have to arrange, factorial, but we divide that. And we divide that by the product of the factorials of the number of times each letter is used. For example, the word smiles. This has 6 letters. And if we pretend there are no duplicates, then we're just talking about 6 factorial. I want a different color here. What do I want? This. Six factorial because there are 6 letters. But there are 2 S's. So we need to account for that. If we want, we can write in that there's 1 M and 1 I and 1 L and 1 E, but that's not really necessary. So we have 2 S's, and we had 1 M. This was because we had a single I. This was because we had a single L, and this was because we had a single E. So again, we don't have to write in these ones, the 1 factorials. They don't change anything. It is necessary that we say it's 6 factorial over 2 factorial. So it's 2 factorial allowing us to account for the duplicates. And if we punch that in the calculator, this gives me 360. So there are 360 rearrangements of that word. Maybe one is like miles. Maybe one is slimes. Maybe one is I don't know. What's another arrangement of this? Lime. Silism. You rearrange the letters. There's like 360 of these. I don't have the time to write them all out. And I'd run out of ink too. That'd be devastating. Gracious. I dare you so hard to try out the other 4 examples here. Try them out, see what happens. Remember, you can pause this video at any point. I'm just going to dive into this. Oh my goodness, Mississippi, it's 1. Now we got here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm going to do 11 on top. And on the bottom, I only have 1 M, so I'm not going to really care about accounting for that. 4 I's. And 4 S's and 2 P's. So this was because of the I. This was because of the S. This was because of the P's. Do be careful when you're punching this into your calculator. Because if you, depending on how your calculator lives its life, if you do this divided by 4 factorial times 4 factorial times 2 factorial, I mean, it's going to do this division first and then the multiplications. So just recommendation, throw that jazz in there. Use those brackets. Brackets are your friends, not food. But keep that there. Why not? So that's how you want to write in your calculator. Hopefully you get an answer that's something like this. Super common error is just punching things into your calculator wrong. For all I know, I did it. I don't know, the number seems reasonable. So I'm going to go with it. Next page. Oh, this person has a lot of pens. This person's a weirdo. JK. It's always good to have extra pens in case one runs out. Oh yeah, why not? Yeah, why not just arrange these pens? That seems like a good use of time. All right. 3 and 6 and 2 and 4 and 1, 10, 13, 14, 15, 16. 16 pens. I count this right. So that's that business. And then we should be getting a value out of that. I don't know. Calculator. Ooh, that's a cute number. Oh, I like this number. That's the number I got. And again, I used 16 up top because we've got 3 plus 6 plus 2 plus 4 plus 1 pens. And then this is because we have multiple purples and we have multiple greens. We have multiple orange ones and we have multiple pink ones. We don't have multiple blue ones, so I don't really care to write down my self-accounting for them. We don't need to show that we're dividing by 1 factorial. The immediate side fam jam. Oh yeah, that's my fam jam. Because, right, my sister has a Civic. I have a Civic. My parents have a Civic. And one sister's husband has, I'm pretty sure it's a Jetta. It's a Volkswagen anyways. And then other sister's husband has some sort of pickup truck. Alright. Pretending that all these civics are exactly same, how many distinct arrangements of vehicle makes are possible? There are 5 vehicles in all. We've got 3 civics, but no duplicates of anything else. So that's that. Here's our total of vehicles. And that's us accounting for civics. Our value here is 20. There are 20 ways. And last one. Oh, Mr. A, drinking all the pop. Now for the record, even though I have all this in stock, I don't drink it that often. I've become a huge water fan over the past few years, so I recommend water all of the time. But in this case, these cans exist. There's 12 cans of iced tea, there's 12 cans of Mountain Dew, 6 cans of root beer, and we're stacking them all the way up. Oh, 1 can on top of the other. Okay, hey, excuse me. Me?
What?
Could you not do that in the middle of a lesson?
Fine.
That would be great. Thank you. Alright, how many distinct stacks are possible here? I will warn you in advance, calculator might have difficulty displaying this one. We're going to have to use scientific notation to represent it, because this number is huge. So, how many stacks are possible? 12, and 6 is 30. It does say we've got 30 cans, so that helps too. But there are 12 iced teas, there are 12 dews, and 6 root beers. Iced tea. That's the one I have to restock the most often. Dew. Only if Ian's coming over for board games. And then root beer. Yeah, I don't have to stock that one as often. It's fine. Punching this into my calculator, I got something pretty close to this, which is the big number. Wow. That's a lot of different ways to stack them. So if I were to try doing every single possibility, I could be at it a while. Hopefully I don't use that in my spare time. I have better things to do, like push-ups. Anyways, here's some questions. It's a gift from me to you. I hope you enjoy this gift. No givesy backsies. But if you have questions, as per usual, please do let me know. This video is done.